Okay, so my plan for the review then is I'm just going to quickly say a few general comments about it, about the in-class test for Wednesday, and then I brought just a few questions for us to kind of practice with a little bit, just to give you an idea. I'm not going to review everything, I'm not going to cover everything. Just because I don't talk about something doesn't mean that you shouldn't look it over. You really should just look over the whole set of notes from the semester. I would focus on the lecture notes, and then when there's any confusions or you need a further, sort of second thing to look at, I would then go to the book. Because if you just try to go to the book to review everything, first of all, I didn't cover everything in the book, so then you're going to be reading some stuff that's not relevant. And I think the notes are going to be more direct to the point of, I'm going to be writing the test based on what came from the notes, not just random stuff out of the book. So there won't be like, I don't like to just ask questions on stuff that I didn't really go over. In fact, the more that I went over stuff, the more times you saw it either in a group work or homework or just me talking about an example, the more likely I would ask about it. So for example, this particular space, the natural numbers where f is closed, if and only if f is equal to n, or f is finite. This is just to give you an example. Here's something that I probably brought up at least 3 times, right, to show you as an example of something. So this is something you want to make sure you understand, like how this example works. What were the things that we did? First of all, we showed that this does form a topology, right? That was kind of the first thing. And then we looked at various subsets of it and talked about whether they were open or closed or whatever, right? So, those kinds of things. If you see something multiple times, it means you're more likely to see that or something like that again on the test. If it's something I just mentioned in passing, or if I didn't mention it at all, it's in the book but I never talk about it, well then I'm not going to ask about it, right? That's not to say that I won't ask you something totally new. Right, I could make a whole new question, but it would have to be something where I believe you should be able to, figure out what's going on during the exam, like even if you didn't study it, right? So sometimes I write a question that I know nobody has studied what it means for a topological space to be connected, for example. That's a new word. We haven't really covered that yet. I could still put it on the test, but at that point I would have to give you the definition. I would have to ask a question that was like very basic and that you could do just based on what I assume you've already studied. Okay. So, and what I'm basically saying is don't worry about it, because you can't study for that because you don't know what it's going to be, right? I mean, you should focus on studying the stuff that you do know that you've covered, that you have seen, with more emphasis on the things that you've seen more often. Okay, so that's what I would do. I would focus on the lecture notes and then supplement with the book as necessary. Okay, I already talked about how I think you should review the group works and the practice quizzes. Go through those, quiz each other on them if you're working in groups. Just draw numbers out of a hat. Group work 2, problem 1. Group work practice quiz 4, problem 2. You do this one, I do that one. Whatever. Just kind of do things that way and work on it and try to help each other out. It'll be out of 46 points. And of course you're learning one of the proofs in detail. That'll be at least about 10 points of the test. So then there's 36 other points, and this is where you want to get as many points as you can. Everything here in these 36 points is going to be, as you'll see from the sample exam, if you looked at that, very simple things, simple examples or counterexamples to certain statements, just a quick justification, something that would take only a couple of lines to explain, or maybe a short proof, and again it would be I would only ask you to prove something that I would think you could prove on the fly. I would not be assuming that you memorized a proof to be able to put it down here. The only proof that I would expect that you would have learned specifically would have been the ones that are on the review sheet. So it's not that I won't ask you to prove anything else. I'm just saying that the other things that I ask you to prove would be things that you should be able to prove even if you didn't specifically study that proof before the test. Yeah.
So you said there's, like, from the 3 proofs, you're going to pick 2, and then
Right.
we pick 1.
Right, right. So, so that means you can figure out, you can decide a little bit what you want to focus on for that. Yeah. Okay, so that's kind of overview of, you know, what this is going to look like. Of course, you'll have the whole class period, and you know, I'll try to give you a little extra time if you need it, but yeah, I think it should be okay. You know, this is where you just want to make sure you know your basics. Make sure you know those definitions. If you didn't get a great score on the definitions on the quiz that we took recently, then you know, you should go back and make sure you review that again, because I might ask you more of that kind of thing as well. I don't like to ask true-false questions. I think true-false questions are tricky and people second guess them, and it's just flustering on an in-class test to do that. I might do something where I say, this statement is true, give me a 2-sentence justification, or I'll say, give me a justification, and I'll give you, the amount of space that I give you to answer a question should be viewed as a hint. If I give you 1 inch to write an answer to something, it's probably not like a whole page explanation. It's supposed to be something with a fast answer, and it probably won't be worth that many points because it's not supposed to take you very long, right? So if something is true, I might say, give me like a brief reason, and give you a little space to write down reason. If something is false, I will say, here is a false statement, provide a counterexample or something like that. And then maybe you have to make up a topological space or whatever. We're going to practice a couple examples of what that might look like here. So, so those are the kind of things that you should be expecting of these 36 points. Some of them will just be simply reciting definitions or propositions. Some of them might be giving an example of this or that, and then some of them might be brief justifications / proofs. That's kind of what you're looking at, okay? And you know, just study hard for it, but also, you know, don't stress yourself out so much. You know, I understand this is tough stuff. I'm not expecting perfection, and you know, you just do the best you can, and we'll take it from there. So, okay. All right. So with that in mind, I thought maybe I would I just have a few questions here to practice on, kind of give you an idea what we might, what kind of things you might see. These are questions that some of them I wanted to put on the test. I haven't written the test yet either, by the way. I always do that like at the last minute. So I can answer any questions and say anything I want because I don't have a test yet to worry about. But some of these things I thought, oh, that would have made a good test question, but actually I want to show it to you guys. So, so let's do some practice, okay? So practice, see how you guys feel with some of this, okay? So here's the first one. So let tau 1 and tau 2 be topologies on a set X. Okay? And then here's the question. Which of the following must also be topologies on X? Okay, so let me give you the first one. So there's going to be 3 of these to practice with, okay? So the first one is going to be tau 1 union tau 2. So if we have 2 topologies on a space and we form the union of those 2, so that means we take all of the open sets from both topologies and put them together into a larger union here. The question is, would that still be a topology? By the way, this might be a nice question I might ask part A, give me the definition of a topology, and then this might be like part B would be to ask this question. So the idea is that I'm suggesting to you that you should think about the definition of a topology for this. So remind me, what's the definition of a topology?
It's the set of an open subset of X such that the subset is a union of the members of B script.
Okay, you're thinking of a basis right
Oh,
now.
anyway.
We're not talking about that. I just want to know the definition of a topology.
It contains X and B.
It contains the whole space X. It contains the empty set. Okay, that's the first part. What's the next part?
There's the union of
Go ahead.
sets and tau
Mm-hmm.
that they are in tau.
Okay, arbitrary unions of sets that are open in tau are still in tau. So it preserves arbitrary unions. Okay, and then what's the other one?
It preserves finite intersections.
Right, the topology has to preserve finite intersections. Nor the way it's stated in the definition is that it has to preserve intersections of two sets. So if you have two sets in the topology, then their intersection also has to be in the topology. Okay, so what I would do with this is I would just start thinking about those three properties of a topology and whether or not they would hold in this case. So for example, so you've got, you know, tau 1 is going to be, it's a set of sets. It's going to look something like that, right? The empty set, the whole space, and a bunch of other stuff, right? Tau 2, you have to have the empty set, you have to have the whole space, and then maybe some other stuff. Okay? Now, if I take the union of all of that stuff, will I still have the empty set in there?
Yes.
Absolutely. So the empty set would be in there. What about the whole space, capital X?
Yes.
Right. Okay, great. So these are both elements of the topology. Notice I'm using element here. I'm not saying subset, because this is an element of that set of sets. This is an element of that set of sets. Okay, so check and check. Those two things are good. Okay, the next one is the intersections. So it has to preserve the intersections of the set. So if I take all of these things together collectively, right, would that be closed under, I know that everything here is closed under intersections, and I know that everything here is closed under intersections. The question would be if I take the union, so I take all of this stuff, if I take any two things in that union, they could either both be from here, or both from here, or one from either place. Would you always end up with something that is in tau 1 union tau 2?
Yeah.
Gosh.
Wait, but the intersection is something that's in both of them, right? That would be in the union, wouldn't it?
Well, we're not. So we're taking like a U here somewhere, some open set there, and then down here there's some open set V, right? Excuse me. So we're asking, will U intersected with V appear up there? So when I take this union, of course, I can already see that I'm going to get the empty set, capital X. I'm going to get U. I'm going to get V, right, and some other things. I'm taking everything that's listed here together with everything that's listed here. What we could think about doing would be asking ourselves if we could just try an example, right? And so you could actually just think about an example, and you know, for these very abstract topology questions, I don't usually like to use things like the Pythagorean metric and R2, or even the absolute value metric and R. Like for something like this where you're just talking about abstract topologies on a set, I just like to do, you know, make my set something like this, right? And then just try to write out a couple of topologies. Let's just see if we can make one up, okay? Let's just make a topology. I think we did this. You've probably done this already, right? Write down a topology on this set here. So I can help you out. You're gonna have those two things. Do you wanna put anything else? Can you put something else in the topology? I'm just worried that this will be too simple. We need to make this a little more interesting.
Apple 1, 2.
The set 1, 2? Okay, now, is that a topology at this point?
Yes.
Still okay. You wanna leave it like that?
Yeah.
Okay, let's just leave it like that. There's our first topology. Okay, let's make up another topology. So again, have to have the empty set, capital X, and
Use 2, 3.
2, 3. Okay, we can do that. 2 and 3. These are two perfectly good topologies. Now let's write down the union. Let's just see what we get. We're going to have the empty set X, 1, 2, and 2, 3. By the way I would probably phrase this question on the test would be, show that the union of two topologies need not be a topology. So then you know you're going to be looking for an example, right? So you're not fishing in the dark for it. Okay, so you have this. Is this a topology?
No.
No, it's not, because it's not closed under the intersect. Like this is the U and this is the V, right? U intersected with V would be just the set 2, which is not in there. So actually, we can stop at this point. Okay, so this is, the answer is no. And then here's our example. Okay. Yeah, so it's something like that. That's a great idea. Okay, let's go on. Let's try tau 1 intersected with tau 2. Let's suppose that we intersect two topologies together. So for example, if I take this example here and I intersect these topologies, now don't intersect the sets. What you want to do is intersect what is common to both of these lists. So the empty set is in both lists and all of X is in both lists. Neither of these two things is in the other list. So in this example, the intersection of tau 1 and tau 2 is the trivial topology, which is a topology. So this would not be a counterexample for us right here. Obviously, I think you guys will all be comfortable that the empty set and the whole set, again, those are going to be fine, right? Because they have to be in both of the topologies. So what do we think here? I think this will work.
We're going to create two different topologies. So we have,
You want to create another example? Okay, so how would we, do you have an idea? Tau 1?
yes.
Go with the empty
We
set.
will have the same one.
Same one for the first one?
The first one, we're going to have phi x comma 1, just as a set 1.
Oh, the set 1.
And then the set 1 and 2.
1, 2.
Yes.
Okay.
I think that's enough. Then we're going to go to the next one.
Go to the next one. Empty set X.
And then 1, comma 1, 2.
1.
Oh no, don't put 1.
Right.
Just the set 1 and then maybe 1 and 3.
1, 1, 3. Does that work?
Yes.
If you intersect these, you get just, you actually just get the first three things, which is a topology, right? Okay, you think it's going to work? I mean, to me, the easiest thing that is not a topology, that does have the empty set and the whole space in it, like the easiest thing is to just do this, like that, right? Because this is not closed under unions. The union of these two sets isn't in my list.
Yes, so we should.
So you would want, right, you would want up here to put that there, right? And then you would also want it to be here.
But then those
are
are
not
not
topologies.
But then these aren't topologies unless I put,
1, 2.
oh, but I have to put it in
Yeah.
both. Which means I actually have to put it here too.
So it just keeps going on like that.
So it keeps going on like that. See, this is the kind of thing, like, I actually didn't think of this problem before. I was just starting to think about it. And yeah, you just play around with it a little bit, and you start to realize that, you know, your counterexample isn't really working the way you would like it to. So what we could do is we could, and again, on a test, I wouldn't be having you go back and forth like this. I would give you a definitive, yes, this works, or no, it doesn't, and tell you which way to go. So if, under normal circumstances though, you would probably have to think to yourself, well, maybe this is going to work now. Let's try it, okay? Let's let U and V be in the intersection of the two topologies, right? So, I just have to show that U intersected with V is still in this intersection. Well, do you see how to do that? Alex?
Yeah, since tau 1 and tau 2 are both topologies,
Yeah.
the intersection of U and V must be in tau 1 and tau 2.
Right, so U and V are both in tau 1. That implies that U intersect V is in tau 1. And you're going to do the same thing for the second one, right? So similarly, and you can say similarly, by the way, guys, just save yourself a little bit of time, especially on the in-class test. You're going to find my grading to be not so strict. And like sometimes on the homework, I really try to mark things up. On the test, of course, I understand you don't have time to write as much. It's got to be as quick as you can. So yeah, you would just write this, and so then we're done, right, Alex? With that part. So tau 1 intersected with tau 2 preserves finite intersections. Okay? So then, the last part is arbitrary unions, right? So this is like I and double I. I get confused. I can't remember whether the book has the primes on these or not. I don't think it does for these, but the triple I condition is, you know, let the set of U sub I, where I is in an index set, be sets in tau 1 intersect tau 2. So you have a whole family of sets that are in the intersection of these two topologies, and then we have to take the union of those, right? Okay, so how do you think we're going to write that one out? Just going to try to mimic what we did over there. What we did over here is we focus only on tau 1 first, right? Just on tau 1. So here we could say, you know, since the set of U sub I belongs to tau 1, which is a topology, then the union, that's right, the union of the U sub i's, right, is an element of tau 1. And similarly, this union of U sub i's is in tau 2. Okay, great. So then the union of the U sub i's is in the intersection of tau 1 intersected with tau 2. Okay, great. So the intersection of two topologies is a topology. That would be yes. Okay. So it doesn't work for unions, but it does work for intersection. Kind of interesting. And then finally, here I can just put part C right here. Part C, tau 1 minus tau 2. Now, this is a set difference, right? One set minus another set. Okay, so you're taking two topologies and you're subtracting. So we give everybody about 10 seconds to think about this one. There might very well be some questions on the test where you just think about this long and then you know the answer. Yannick, what do you think?
It's not.
It's not. Why not?
For example, if you subtract x with x, we don't have any x left, so.
Exactly. So this is like an easy one. This is an easy one, right? Both of these sets have the empty set and all of x in them. So when you subtract them, you can just say the empty set is not in tau 1 minus tau 2. You're done, right? I think you want that one on the test, right? It's a pretty nice, pretty simple one to write
You
down.
subtract the empty set from the empty set?
Empty set minus the empty set.
What do you-
You are, yeah, you're subtracting. You're taking the empty set out from whatever the topology is that it was a part of. So you know you have tau 1 has the empty set x and some stuff. Tau 2 has the empty set x and some stuff. And when you subtract these, you're taking these sets out, right? So the x and the empty set will not belong to that set anymore.
Okay, I was just thinking like the empty set minus the empty set.
Right, you're subtracting nothing from nothing.
Well, I thought like if you could have like the empty union, or and that would be just like nothing.
But that, you're thinking along the lines of like building new sets by taking unions of things, whereas I'm just thinking here more, I'm not really thinking of like a basis concept or anything. I'm literally just looking at my list of sets that are in here, and I'm realizing that I just took out the two most important sets in any topology. Right. Okay. Let me give you another one. Number 2 here. I just want to give you the flavor of what kind of questions I could maybe ask. So here's number 2. Okay. If XD is a metric space and F contained in capital X is finite, capital F is a finite subset, then show that capital F is closed. Finite sets are always closed. That's what we're saying. That's what we're saying. By the way, it could also be open. Remember, open and closed are not exclusive. You can have sets that are potentially both. So don't think about whether F is open or not. You can think about openness in a certain way, but whether or not F is open, we can't address with just that much information. Okay. To show that F is closed,
So bottom line of empty element.
right, you guys are all thinking exactly the right way, which is you look at the complement, right? And you try to show that that is actually open. I'm going to make a suggestion here before we do that, though, is I'm going to suggest that we assume that F has only one element in it. Think about this. Any finite set is just a finite union of singletons. Right? The finite set is just a finite union of singletons. And remember that closed sets are preserved under finite unions. So if I can just show that a singleton is closed, it's going to be easier. That's why I'm doing that. If I try to just take the complement of F the way it is right now, it's going to be a little bit more messy. The idea will be basically the same as what we're going to do, but it's cleaner and easier to just assume that F is a singleton. So for my proof here, I'm going to say that we prove this